Hi. In this problem, we're going to look at how to use the central limit theorem to estimate the probability of making a wrong decision. And the decision that we're trying to make in this problem is to decide whether or not a roulette wheel at the casino is fair or not. So a roulette is just a game at the casino where there are a bunch of numbers on a wheel. You put a ball, you spin the wheel, you throw a ball onto the wheel, and you bet on which number the ball is going to land on. So in this case, we're going to deal with a wheel with 36 numbers, 1 through 36. And we're going to try to estimate, or we're going to try to tell whether or not this, this roulette wheel is fair. OK. So the way we're going to do that is we're going to observe what number the ball lands on for 100 times. And our decision rule is going to be, we're going to look at how many times out of those 100 the ball lands on an odd number. So there's half odd numbers, half even numbers. And if it's fair, we would expect that about 50 times out of 100 it'll land on an odd number. And so our decision rule is going to be, if more than 55 out of the 100 times the ball lands on an odd number, we're going to say that the roulette wheel is not fair. OK. And now what we want to know is, given that rule, what's the probability that we'll make a wrong mistake? Meaning that more than 55 times out of 100, the ball lands on an odd number, but in fact, the roulette wheel actually is fair. OK, so what we're going to do is we're going to assume that the roulette wheel is fair, meaning that all the 36 numbers are equally likely to be landed on. And we're going to test, or we're going to try to calculate what the probability of making a mistake is. So let's define a random variable. Let's call it S, where S is a number of times you get an odd number out of 100. And so we assume that also that each of the times you play this game, it's independent. And so what we have is that this is just the number of times you have a success, where we can define success as being you get an odd number. And so then S is just a binomial random variable, right, where you have 100 trials, and the probability of success on each trial, because we assume that the roulette wheel is fair, is 1/2. 50-50 chance of getting an odd versus an even number. And so because of that, we know from binomial random variables that the expectation is just n times p. N is 100, p is 0.5 here. So you expect to get 50 odd numbers. And the standard deviation of S is, for binomial, it's the square root of n p1 minus p. In this case, it's 100 times a half times a half. So it's a square root of 25. And so the standard deviation is 5. And now, because if you actually wanted to calculate the probability that you'll make an error, well, how do you make an error in this case? We assume that the roulette wheel is fair. So in that case, you'll make an error if you actually do get more than 55 odd numbers. And what is the probability of that? The probability that what you're looking for is the probability that S is greater than 55. If this event occurs, then you will make a mistake, because you will say that the roulette wheel is not fair when in fact it is. OK, so how do you calculate this? Well, you can calculate it using the actual binomial PMF, and what it amount to is a big summation. So it'll be the summation of, you have to get anywhere between 56 to 100 odd numbers. For each one of those, there's 100 choose k ways in which orders in which those k odd numbers can appear out of the 100 trials. And then you have the probability of success is a half. Probability of failure is also a half. And so because of that, it just simplifies to a half to 100. So this is just the standard binomial PMF, and you just take this summation. Now, this is kind of complicated. And so what we're going to do is look for an approximation to this using the central limit theorem. All right, so there are different ways of doing this, and we'll actually go through 3 different ways of doing this. The first one is, well, the probability that we're looking for is this. And so we do the standard kind of converting to a standard normal. So what we do is we subtract the mean. We subtract the mean and divide by the standard deviation on both sides. And then we invoke central limit theorem, and we say that this is, well, this is approximately probability that z, the standard normal, is greater than, well, this is 5 over 5 is 1, which is just 1 minus phi of 1. And if you go in the standard normal tables, you can find out what phi of 1 is. Turns out it's 0.8413. And so the approximation that you get here is 0.1587. So this is your approximate probability of being wrong, saying that the roulette wheel is unfair when in fact it is fair. Okay, so notice that we've actually used 55 here with the strict equality, right? And because S is a binomial, this is fine, because it turns out that this probability that S is strictly greater than 55 is exactly the same as the probability that S is greater than or equal to 56. Because S is binomial, it's discrete, it takes only integer values, it can't be anything between 55 and 56. So these are actually the same. So we can take that and now use 56 in our central limit theorem approximation. So what that tells us is this is now, we can rewrite it as this, 56 minus the mean over the standard deviation. So because this is, now because this is, when we take this conversion and invoke the central limit theorem, what we'll get is that this is approximately the probability that z is greater than or equal to 6 over 5 or 1.2. And this is, again, of course, 1 minus phi of 1.2. And then if you look in the tables again, this is approximately 0.1151. So with 55, we got 0.1587. With 56, we got 0.1151. They're not too different, but there is kind of a fairly significant percentage change between the two. So which one is right? Or is there even an even better way? Some kind of middle ground. And that is exactly the third way of doing it. And this is also the Demoivre-Laplace approximation to the binomial. So instead of taking just strictly either the two integer values, 55 or 56, what we do is we take the middle ground. And we say that, well, let's instead say, approximate this with the probability that z is greater than 55.5 minus the mean over the standard deviation. So that would give us, this is 1 minus now phi of 1.1. 5.5 over 5 is 1.1. And if you look in the tables, this will give you 0.1357. So we have 3 candidate answers. This is the biggest, this is the smallest, and this is in between. So it turns out that if you actually actually calculate out this summation, the exact answer, or the exact answer at least to 4 decimal places, is 0.1356. This is without any approximation. You actually calculate the exact probability using the binomial distribution. And you can see that the midway point approximation, the Moivre-Laplace approximation, is very close to the exact answer. And so this is, in general, the case, especially when you have when n is large and p is roughly equal to half. So when you have a roughly balanced binomial distribution with enough samples, then using this midway point approximation will be better than using either of the 2 endpoints. Okay, so this is just an example of applying the central limit theorem and specifically applying it to the binomial distribution. And you can see that there's different ways of doing it, and in some cases, using the midpoint approximation gives you a better approximation. Okay, I hope that was interesting, and see you next time.